to do was to create a free body diagram of the system. So we did this on flat ground and also on an incline. So the forces to consider are friction, which acts in the forward direction of velocity on the back wheels. This is driven, and then in the reverse direction of velocity on the front wheels. Normal forces act up on both points of contact on the wheels, and gravity is acting down. So some important things for us to consider were the position of the center of mass, which depended on the position of the motor and the battery, the coefficients of kinetic friction between the wheels and the ground, radius of the wheels, the size of the wheels, and then of course the torque and the RPM.
So based on other groups' data, we estimated our mass and the length of our car at like 200 grams and 6 inches respectively. And we also took into account the length of the rear wheel towards the center of mass, which is obviously affected by the motor and the battery. And from that, we were able to test a few different things that affected our car. The first thing we checked for was the size of the radius of the rear wheel. And in general, we got a graph that showed that increasing the radius decreased the overall time it would take for the drag racer to finish. There was a point of inflection, which we thought was important to cross, so when we were designing, we definitely wanted our wheels to be greater than 1 inch. The next thing we tested was which of the 4 gear ratios would be the best for our car. This is a graph of normal force on the front wheel, which we wanted to decrease so the car didn't flip over. So as you can see from this, ratio A, B, and C are all quite low, so they're all viable choices to make. And the last thing we tested was essentially what the best theta, or the best angle to run our car at was. And we got an interesting result saying that our car could go up to 30 degrees. This actually didn't work out in practice because the model is quite idealized. But it also did show that at 45 and onwards, the car actually did manage to complete the slope.
Characterization graph, we needed 2 points on the graph, so we used the y-intercept, which was the maximum torque with 0 RPM, and then the x-intercept, which is maximum RPM and 0 torque. So to get the maximum torque, we had to stall the motor against the scale and read the mass that it read on it. So to do that, we pushed the motor connecting shaft against the scale until it wouldn't spin, and we read what that mass was and then multiplied by 9.81 to get the force of gravity. And then to find maximum RPM, we used the tachometer and let it spin with no added weight, so the balance of forces, there was no net torque on the system, and it read 1472 revolutions per minute. So using slope-intercept form, we graphed this graph on MATLAB for the given gear ratio. Some things that didn't work were that our car did not manage to run on an incline. It only ran really fast on flat ground. So some reasons that might have been were because of stripped gears, also wrong coefficients of friction on the wheels, and due to the position of the battery pack was too far forward, so that we